OK，那就开始。呃，我这样说都听得见是吧？喂，宇浩，
哎，可以，能听见
可以啊，可以啊，OK
啊
OK，开
啊，
始啊。今天讲一下这个李群和李代数啊，就是一个听上去很高级啊，实际上也没啥。就是我觉得学数学这个东西，就是第一点就是不要怕，你不要被这种高端的名词给吓到了。然后你每次遇到这种名词，你可以把它换成一个，比如说你管它叫李四群、什么张三群什么之类的，你就不要被它吓到，然后你就学就是了啊。反正就是开头先说两句，然后讲李群和李代数，先给他们下一个明确的定义吧。就是李群，它首先你看它名字里带一个群，就是所以说它一定是个群嘛。同时，它还是什么样的群呢？它是一个满足流行性质的一个群。就这句英文的就是很出名的一句话，A league group is a group which is also a manifold，就上面这句话就是翻译嘛，就是它既是一个群，也是一个流行。那么首先先问肯定会问了，什么是群呢？什么是流行呢？首先群这个理论可能大家也听说过一点儿，就是他是法国的一个非常出名的一个天才数学家。叫嘎罗瓦。你看他是1811年出生的，他死的时候是21岁，非常英年早逝。他怎么死呢？他是和别人决斗，就是为情而亡，就是和情敌决斗，被枪给杀了。你看他21岁，他就已经开创了一个可以说数学领域里非常非常重要的一个分支吧，就是群论。甚至可以说群也可以叫嘎罗瓦群，就是这整个理论都是由他来命名的，可想而知他有多么厉害了。所以说，当时他为什么发明这么一个理论呢？他是为了解决什么问题呢？他是为了解决这个问题，就是一元五次方程有没有根式解这个问题。其实这个问题在数学界在那个年代已经400年没有解了。就是说，一元二次方程你可以写出一个非常明确的根式解，咱们初中啊都学过。然后其实一元三次方程也有一个更复杂一点的根式解，一元四次方程有一个超级复杂的根式解。当时人们就问了，哎，那一元五次方程有没有根式解？之所以找不到，是不是因为它太复杂了，所以我们找不到？但它实际上还是有的。然后嘎瓦罗通过他自己创造的这个群的理论，就通过对称的理论。简单来说就是你不是一元二次方程能解出两个根来吗？这两个根之间它互相交换位置，它可以仍然满足一些等式关系，这就是一种对称性的一个体现。一元三次方程的3个解也可以在一定程度上满足对称性。它证明了一元五次方程它满足那个对称性，根据群的理论所形成那个表，它不是可以拆分到最小的那个单元上的。这个可能我讲起来有点云里雾里的，这个以后有机会单独给大家讲，这不是今天的主题。就总而言之，群就是一个关于对称性的一个理论。你看，它可以互相交换，就这个就是完全不交换，这个就是1和3交换，2和4交换，就是你可以找出各种各样的，就几种操作方式，然后这一组操作方式构成一个群，然后你就可以给这个群命名，比如说什么C3群什么之类的。然后对，我们初中、高中学的那个排列组合的那个 C 和 A 也是群里面的概念，就是群里面的概念。然后，那什么是流行呢？流行它的英文名是 manifold，然后这是日语，这多面体啊，多面体。我这是单独把日语的这个名称给放进去了，因为我感觉其实日语的这个是最准确的，最准确能帮助你理解的。什么是流行呢？你看右边这张图，它是一个球，你可以把它想象成一个球面，然后这个球面它的各个方向的曲面可以映射投影到一个平面上，就类似于比如说这个黑的圈儿是个地球， 你可以看到，比如说有个亚洲地图是这样的，有个美洲地图是这样的，就类似的，就是说你想想，你看到的世界地图，它实际上虽然它是个平面，但实际上是一个曲面的一个映射。就流行就是这么一个，就是讲，就相当于是一个地图的一个学说，它讲的一个拓扑空间上，在每个点附近，它的局域都可以类似获得一个欧几里得空间。什么叫欧几里得空间？就是平的，一切都是平的，x、y、z 都是非常非常平坦的一个空间。你看，在地球上，尽管地球是一个曲面，但在一个点附近，你总是可以把它看作一个近似的一个平面。这就是流行的一个主要，可以说主要概括吧。然后“流行”这个词儿是怎么来的呢？其实是当年数学家就是翻译的，他借用了文天祥的《正气歌》里边第一句"天地有正气，杂然复流行"，用的"流行"这个词儿，算是一种数学家的浪漫吧。但是其实这个词儿挺容易让人误解的，让你感觉它可能和流体啊什么之类有关系，实际上。有关系，但是没有那么直接。后面我还会讲到关系到底在哪。然后，所以说你可以看到群是这么一个学科，流行是怎么样一个理论。群是一个关于对称性的理论，流行是一个关于连续的映射的一个理论。同时，对称性我们又可以把它，我们又知道它是和守恒是等价的。连续的映射，我们又可以把它理解为变化。所以说，你看这两个概念，守恒、守恒量、变化，怎么样的变化？你看这是不是非常的和物理非常非常的关系非常非常的密切？如果你再把这两个理论结合起来合体，你可想而知这个理论在物理学里能有多么大的用处。事实上，就是李这个人，就是一个挪威的一个数学家，他当年发明这个李群这个概念的时候，他是想仿照伽罗瓦的这个群的概念，因为伽罗瓦证明了那个一元五次方程没有根式解嘛，他想讨论一个方程，一个偏微方程有没有解，有没有什么形式解的这么一个问题，他仿照他去做了一个理论。就尽管他这个李群对于有没有解其实没有什么帮助，他研究的方向其实是错的，但是他创造出来这个东西，发挥了他根本没有想象到的非常恐怖的、非常巨大的威力。也就是说，就是李群这个东西，其实在物理学里可以说是最出名的数学理论，没有之一。就是它既是最有意思的数学理论，也是最出名的数学理论，可以说是每一个物理学家都应该学的这么一个数学理论。那么你看，我这里指的只是在讲李群，但是我的标题又是李群与李代数。那李代数去哪了呢？这里我给一个有点抽象的一个等式哈。李群实际上就是你在一个一指数上放上一个李代数。就初学李群，大部分教科书都是在教一个李代数对应怎样一个李群。你可以看到李群和李代数是一个一一对应的一个关系。那么你就说，这个一指数上放一个东西，这是什么概念呢？好了，这个下面就请看 VCR，就是就是从油管上搬的一个视频，然后自己配了字幕，然后这个人讲的很厉害，他是剑桥大学的一个数学硕士，对，他很厉害，他在油管上粉丝也有几十万。我剪的视频自己翻译的，大家可以看一下。
We often think of exponentiation as a rapidly growing function or a rapidly shrinking one depending on the argument. This is just exponentiating real numbers, but of course, you might have heard of exponentiating complex numbers. However, it is possible to define exponentiation of many other things, including vectors, ddx, or any other differential operators, as well as an entire vector field. Just to be clear, these are not hallucinated by mathematicians, they have concrete applications in other areas of maths. These exponentiations, as I will explain later, are really different at first glance. So, why do we use the concept of exponentiation to lump them together? To answer the why and really understand these weird exponentials, we first need to revisit what exponentiation really is. If you ask different people what exponentiation is, you will get at least three different kinds of answer. A function whose derivative equals itself with the extra condition that exponentiating 0 gives 1, or that it has a series expansion as shown here, or very often as a first introduction as interest rates, the limit of a certain expression. For this video, I'm mainly going to use the derivative property of the exponentials, but we modify this definition a little bit. We instead consider another function g of t that satisfies another set of related conditions. Don't worry, g of t would actually just be exponential of tx, and the conditions here are just what we expect exponential of tx should satisfy. Then e to the x is simply plugging in t equals 1. Now, this is quite a neat way of thinking about exponentiation because rather than thinking of e to the x as a single point, g of t forces us to think of e to the x as the endpoint of a journey. More specifically, this journey starts from g of 0, which according to our conditions would be 1. And we work our way towards the endpoint, which is going to be e to the x or g of 1. So exponentiation can be thought of a little more dynamically. It is actually a journey, a process. Of course, this journey, g of t, is not just a random journey. It still needs to satisfy this condition of g of t. This condition tells us that initially the velocity is x because the conditions imply that g prime of 0 is x. Then at any intermediate point g of t during this journey, the velocity is x times g of t. To find the exponential of x, we stop when we reach 1 unit of time to get g of 1. Now, something that will be useful later on is to notice the setup at the start and the intermediate points along the journey. The initial setup includes the starting point, which we choose to be 1, and the initial velocity x, which is something that we try to exponentiate. To go from the initial setup to the general setup in the middle of the journey, we simply multiply the whole initial setup by the current position g of t. The exponentiation of x is then the endpoint of the journey after 1 unit of time has passed. Thinking of exponentiation this way might not be new to you, but this framework helps us understand how to exponentiate more exotic objects like vectors, derivatives, and vector fields. Let's start with how typically mathematicians exponentiate vectors. In the context of manifolds, which I have briefly introduced in the previous video, mathematicians have defined the exponential map for vectors. To define the exponential map, the vector needs to be a tangent vector on the manifold, and the result would be another point on the manifold. But why do we choose this point? Here, I'm using the two-dimensional surface as an illustration, but actually it could be generalized to higher dimensions. First, think of this vector v as an initial velocity vector, and you are initially traveling from the point P. After traveling for even just a moment, we can no longer travel at the same exact original velocity because this initial velocity vector is not tangent to the surface anymore. We still want to kind of travel at this velocity, so we make a slight adjustment. Simply rotate the vector so that it is now tangent to the surface again. A little more technically, this rotation is such that the rotated vector coincides with the projection, or the plane containing the unrotated and rotated vectors is perpendicular to the tangent plane. But in any case, the spirit is to make minimal adjustment to the initial velocity vector to make it tangent again. So this rotated vector is our velocity from this point, say q, onwards. But of course, we face the same problem when we proceed. This already rotated vector cannot be the velocity even just a moment after, and we need to do the same little rotation to make it tangent again. So we actually need to continuously slightly rotate this initial velocity vector along the way. This process of continuously rotating a tangent vector along the way is called parallel transport. But for the sake of exponentiation, when should we stop this parallel transport process? Recall that we are trying to exponentiate this vector v, which has been described as the initial velocity. We let this go on for exactly 1 unit of time. Wherever we end up would be defined as the exponential of v. The notation here has a subscript p under exponentiation to indicate that the whole process starts at the point p. But what is exponential about this process? Compare this with the exponentiation of normal numbers, where the initial setup indicates a particular starting point and initial velocity, and the intermediate setup is obtained by simply multiplying the entire initial setup by the current position. The exponential is the endpoint of the journey when 1 unit of time has passed. For exponentiation of vectors, this starting point is now changed to p, a specified point on the manifold. The initial velocity now is really a velocity vector v. This is also the thing that we try to exponentiate. To go from the initial setup to the intermediate setup, this time we parallel transport instead of doing any multiplication, so that this is the intermediate setup. Very similar to the case of normal numbers, we stop the process after 1 unit of time. The end result is the exponential of the initial velocity. Now, some of you might be thinking there is something wrong if this is meant to be generalizing exponential of normal numbers. Let me explain. If we consider a specific case where the manifold is just a plane, or even simpler, just a number line, then throughout the process of exponentiation, in particular the parallel transport process, would just be a normal translation. This is because there is absolutely no obstruction to traveling with this velocity on a flat surface, so we don't need to rotate to keep it tangent. So with the parallel transport just being a translation, the velocity in the intermediate setup is still v in this case, same as the initial velocity. But this is at odds with the exponential of normal numbers because the initial velocity and the intermediate velocities are, in general, different. Now, there are 3 different levels of resolutions to this problem. The easiest level is to simply say that they are completely separate things. They are only spiritually similar. One is not necessarily a generalization of the other. The second level is to recognize that on the complex plane, we can restrict ourselves to only thinking about the unit circle centered at the origin, and always start at the point 1 as you do for exponentiation of normal numbers. A tangent vector at 1 can be identified with a purely imaginary number, say I theta. This is because in general, for any complex number, we can identify it with a vector emanating from the origin towards that complex number. So in the case of an upward vector, it corresponds to a purely imaginary number I theta. So with a tangent vector being described as I theta, if we exponentiate the vector during the parallel transport along the circle, we will get a point which actually is e to the I theta in the complex number sense. So at least in this case, they are not just spiritually connected, they are literally the same in this case. The third level is that they are actually connected. Exponentiation of vectors in terms of parallel transport really is a generalization of the normal number case. But to really understand the connection at this level, we need more advanced concepts in differential geometry, which is a story for another time. For now, just know that to exponentiate the vector v from the point P, we simply parallel transport the whole setup and stop when 1 unit of time has passed. Okay, so this is how we can exponentiate vectors, but what about derivatives? The derivative itself is an operator, which means that it takes a function as input, in this case the squaring function as illustrated, and outputs another function, which is the doubling function as illustrated. The exponential of d dx that we are going to define is also an operator, but we will see how an input function f of x changes to the output function g of x under this exponential operator. This time, we go back to exponentiation of normal numbers and see how we can modify it to exponentiate derivatives as well. For the initial setup, what should be our starting point? It would make a lot of sense for it to be our input function, say f of x. The initial velocity is something that we exponentiate, so this should be a derivative. In this case, it should be a derivative acting on our input function. But hang on, what do you mean by a velocity being a function? Visually, we can think of a function as its graph. Here, I'm plotting the graph in a 3D space just on the vertical plane. This vertical plane can be thought of as the time t equals 0 slice, and we evolve this function f of x in time. This is the journey that we need to take for exponentiation. More explicitly, this time the journey g of t for a fixed t equals t naught, g of t naught is itself a function of x, which you can think of as a snapshot when the function is evolving. Because g of t naught is a function of x, it makes sense to think of it as g of t naught x, so that g is simultaneously a function of t and x. And along the journey, we simply increase the value of t. Okay, so the initial setup is now from g of 0x, being the input function f of x, and somehow the rate of evolution of this function is its derivative. What does it mean? If we fix the value of x and simply let it evolve like before, then this point will also make its own trajectory. When we say the rate of evolution is the derivative of f at the start, we mean that initially the height of this point changes at a rate of f prime of x. Equivalently, the slope along the t direction is f prime of x initially. So this explains the initial setup, particularly what it means for the velocity to be a function itself.
我
But
这是有点 Q
what
了。
should the intermediate setup be? If we go back to the exponentiation of numbers, rather than thinking of multiplying the whole initial setup by some number, alternatively, we can think that the velocities are actually x times the current position. So in the case of exponentiating derivatives, the initial velocity is the derivative of the input function. It would be natural to take the intermediate velocity to also be the derivative of the current function. This is the spirit, but we need to be careful with our notations. First off, we have already been thinking of g as a function of both t and x, so we need to adjust the current function to be g of tx. The derivative is denoted using a partial derivative, which might not be familiar to you, but basically it means that if we
好了，
fix t, this is a snapshot function of x, then take the derivative with respect to x. In fact, a shorthand for this intermediate setup is this equation involving partial derivatives. The left-hand side denotes exactly our notion of velocity in this context because The velocity in this context also starts by fixing x and tracking its velocity when it evolves. So the velocity is really fixing x and taking derivative with respect to t. Finally, the result of exponentiation would be g of 1x after a unit of time has passed. But can we write down this exponential more explicitly? It seems like we need to solve this partial differential equation, which you can, but you don't need to. After all, this partial differential equation just means that the slope along the t direction, that is partial g partial t, is the same as the slope along the x direction. So if you compare going towards the x direction by a very tiny amount, say epsilon, versus going along the t direction by epsilon, since the slopes are the same, in these two situations you end up with roughly the same height. You can think of going along a sort of 45-degree angle, and at least for a short time, you are not going up or down. But of course, this is not just at this point. For any other point, we can still run through the same argument. And again, going along this 45-degree angle, we are going level. So in general, going from the time t slice to time t plus epsilon slice, we simply have to translate along this diagonal direction for a tiny bit. However, once we are on this new time slice, we can basically use the same argument because we still have this partial derivative condition. So during the whole time evolution, because of this partial derivative condition, we can actually think of it as a simple translation. Thinking about it this way could directly help us kind of solve the partial derivative equation. At a particular time slice, we can obtain the value of g of tx by simply tracing back where it comes from. At time t equals 0, the function is f of x, our input function. And the point when we trace back where g of tx was translated from would be exactly the point f of x plus t, because the 45-degree translation means that you have translated t units along the t direction and also t units to the left along the x direction. Because the whole thing about this translation is that it stays level, we have these two being the same, i.e. g of tx is equal to f of x plus t. If we go back to the exponentiation, which is what this whole thing is for, ultimately we want g of 1x, which according to this result we have just derived, means that the final destination is f of x plus 1. So what exponential of d dx does to a function f of x is to shift the argument in the function by 1. In fact, more generally, because we have this relation g of tx equals f of x plus t, and g of tx is supposed to be exponential of t d dx acting on f of x, we have this more general statement about exponentiating derivatives. This operator is typically called the shift operator because it simply shifts the argument of the function by t. But this shift operator can be more general, especially for multivariable functions. For functions with two variables, the shift operator would be composed of partial derivatives, and the partial derivative with respect to x would shift the x argument, and the one with respect to y would shift the y argument. This can be further generalized to higher dimensions with more variables and partial derivatives, but it's usually succinctly written like this. This more succinct equation is often seen in quantum mechanics, and in the context of quantum mechanics, this exponential of derivatives is called the translation operator. However, the exponential can act on something other than d dx and linear combinations of it. The whole discussion hinges on the intermediate setup being a partial differential equation. The reason why the velocity of this journey through functions is partial g partial x is because we are exponentiating d dx. If we want to exponentiate, say, the second derivative, then this equation would have changed to the velocity being the second partial derivative with respect to x. Of course, in that case, the initial velocity would have also changed. The intermediate setup, as we discussed, has changed, and at the end of the journey, we would have the exponential of the second derivative. But this time it will not be f of x plus 1, it would be whatever g of 1x is, when g satisfies this differential equation and g of 0x is our input function f of x. More algebraically, in this exponentiation of the second derivative, we are finding g of 1x, where this g satisfies a differential equation and an initial condition. This was our previous endpoint of the journey. The equation is what we have been calling the intermediate setup, and the initial condition is the starting point of the journey. Of course, it is not limited to the first or second derivative. Any differential operator h hat can be exponentiated in a similar way. Just replace the right-hand side of the differential equation by h hat acting on g. In fact, more generally, if we are not just thinking of the endpoint, then the intermediate function's g of tx is represented by the exponential of th hat acting on f. Now, throughout this chapter, we focused on the case when the operator is d dx, and this differential equation has a simple solution. G of tx equals f of x plus t. However, for general operator h hat, there might not be such a simple solution. In this case, the exponential of th hat acting on f of x works as a formal solution, so that you don't always need to write down the full set of equations and initial conditions just to refer to this function g of tx. Just a word of warning though, this h hat should be independent of t. Of course, as a differential equation, it could depend on t, but the formal solution here wouldn't work if h hat depends on t. If instead the equation has the operator depending on time, then the formal solution would have been way more complicated, and it is not exactly an exponential anymore, but something called a time-ordered exponential. But in any case, now we know what the exponential of derivatives mean. It is just a solution to the differential equation subject to the initial condition given by the input function f. A vector field is obtained by attaching each point in space with a vector. I'm just showing some vectors here to avoid clutter, but in theory there is a vector attached to every point. This can also be exponentiated. The result would be a function that takes a point P in space to another point Q, which would be the exponential of the vector field acting on P. How does the exponential work? Well, we just go back to the exponential of normal numbers and see how we can tweak it to exponentiate vector fields. For the initial setup, we can choose the starting point to be the point P in space, and the initial velocity to be the vector attached to that point. So visually, we start off at a point in space P and just see what vector is attached to it. This will be our initial velocity. Now, in the intermediate setup, we should have the velocity to be the vector attached to the current position g of t. This is because in the normal numbers case, the velocities in the initial and intermediate setups have a very similar relationship with the current position. In this number case, the relationship is that the velocity is multiplying the current position by x. So in the vector fields case, both setups should be similar, which would be that both velocities are vectors attached to the current position. And again, the endpoint of this journey, after 1 unit of time has passed, would be the exponential of the vector field acting on P. The whole setup is basically asking us to treat the vector field as velocities at the different points. So visually, we start at a point P. Then we follow the vectors in the vector field and treat them as velocities. The trajectory here is the journey g of t. The destination, when 1 unit of time has passed, would be where the exponential of the vector field takes us from P. In general, the intermediate points are also described by the exponential of t times the vector field, where you can think of each vector in the vector field shrinks by a factor of t. The exponential of this family of vector fields is aptly called flow, because it really lets the point P flow to other places along this vector field. There is one kind of vector field in particular that will be useful later on in the video series, a linear vector field. This is a specific kind of vector field in which the vector attached to each point is related to its position. Pick a particular point, we can associate it with a vector emanating from the origin. Call this vector x. Then the vector attached to this point is ax for some matrix A. If every vector attached is constructed with the same matrix A, then this vector field is a linear vector field. Because the vector field is constructed with the matrix A, it would make sense to abbreviate this whole vector field to just the matrix A. So when we try to exponentiate this particular vector field, as usual, we consider how it flows. More precisely, given a random point with the associated vector emanating from the origin being v, the flow along this vector field is going to be described by an exponential. The resulting vector is going to be exponential of t times the vector field acting on v. However, in the case of a linear vector field, we can simply abbreviate this vector field as the matrix A. This is actually how we exponentiate matrices. This idea of exponentiating matrices viewed as vector flows has been presented on 3Blue1Brown's channel as well. In fact, equipped with this intuition of matrix exponentials, it is possible to intuitively understand this exponential relationship between determinant and trace. But of course, we need to understand the intuition of trace first. Again, that's a story for another time. So exponentiation of lots of exotic objects really stems from this journey framework. The exponential of vectors involves the idea of parallel transport to go from the initial setup to any intermediate setup. Exponentiating derivatives requires the intermediate setup to imitate the initial setup in the sense that both velocities are derivatives of the current function with respect to x. And for vector fields, the intermediate setup also imitates the initial setup so that both velocities are just vectors attached to the current position along the journey. And that's it. I'm sorry that I have been away on YouTube for a long time, so a really big thanks to the patrons who are still supporting me. As usual, like and subscribe if you enjoyed the video, and I will see you next time.
OK，继续啊，继续，嗯我不知道大家还在不在啊，但是我就继续讲下去了。首先这个视频里你可以看到，它对3个东西进行了求异指数运算，然后其中分别是矢量、算符和矩阵。实际上，如果你学过一点儿量子力学的话，你就会知道这3个东西在某种意义上是等价的，矢量、算符和矩阵。然后 但是今天我主要讲矩阵这个思想，因为我想把它引入到咱们学的这个东西里，就是说咱们搞物理海洋的，为什么非要学这个李群这个东西？首先我在这儿放一个 n 次方程，只有 u 和 v 水平流速 u 和 v，这样比较简洁一点。你看到这边 d dt 大 D，然后 fx 就是 f 在 x 上的外力在 x 上的分量，然后你可以把这个 d/dt，你看你可以把这两行方程用一个向量的形式，一个矢量的形式，给它分解成变成一行，你看 d/dt 等于 fx，所以说第一列这儿这一列就是第一行，这一点就是第二行。你可以再把这个 d/dt 给拆开，拆开之后你可以变成这个形式，这偏偏 tu 等于这个矩阵乘以 uv 加这个矩阵乘以 uv。你可能感觉奇怪，这是什么玩意儿？实际上你就是用线性代数的知识，你就可以知道，这里就是 ux 乘以 u 再加上 uy 乘以 v，这不就第一行那个偏 u 偏 t 后边紧跟着那个东西吗？这也是 usu vyv 等于 fx，就是 n 次方程，只不过给它换了个形式而已。然后在这里很自然的，我们先把这个非线性给消掉，然后为了方便直观一点，我们先也不考虑外力了，就说外力是0，0，然后单纯就看这么一个方程。这个实际上可以理解为一个背景流对你要研究的那个运动的一个非线性的一个影响。你把这个矩阵，我把这个矩阵单独拎出来给大家看一看，它长这个样子。然后其实我可以把它分解成四个矩阵，就像矢量分解一样，你可以把一个向量、一个矢量分解到 x、y、z 三个方向上，我可以把这个矩阵分成4个单位矩阵，大家看一下，哎，分成了这么4个单位矩阵。你可以自己算一下，这是不是这4个东西加起来是不是等于之前这个矩阵？然后你可以看，哎，分成这4个之后，你首先看一下这个矩阵长什么样。这个是单位矩阵，你看1100单位矩阵，什么都不变。这个长这个样0-110，这个长0110，这个是100-1。然后你再看它前面的系数，哎，这是什么东西？这不是散度吗？散度的1/2，这是什么东西？这不旋度的1/2吗？这不是应变的1/2吗？这不是一个应变，另一个应变，应变不是有2种吗？你可以写成我们比较常见的这个形式：1/1d、1/1z，对，它2/ss、sn，是它们每个都有自己的名字嘛？散度、旋度、剪切应变、法相应变。实际上，你想如果你还记得你学流体力学的时候，你会想起来，流体它就这4个属性，就是一般的，就是你光考虑二维平面的话，它就是这4个量。然后我现在给大家再从这个，我想往李群、李代数上靠吧。我现在假设这3个，我们先不看它了，我们就先看这个比较常见这个旋度。哎，你可以看这个其他那3项扔掉了，然后这个偏 u 偏 t 就只等于-1/2 zeta 乘以它这个矩阵 uv。为了我再回到刚才那个，给大家再看一眼哈，原先这个式子是长这样的。这个矩阵不是拆成了4个吗？我现在只保留其中一个，OK，然后再往下，对，它只保留其中一个，它就长这个样。长这个样之后，哎，其实这个形式其实让你有点想起什么东西来了。你看偏偏 t uv 等于一个什么东西乘以 uv，你想想，你学数学的时候，这个形式不是最好求解的吗？我现在把这个式子往上一放，然后我一解出来啥？就是个一指数啊，一指数是前面乘以一个系数，再乘一个 t，ab 是任意常数。你看，这变成一个从原先这是一个要求解的方程，我解出来的解是这么个形式。你看这个一指数上面放了个什么？放了个矩阵。 就是刚才那个视频讲的第三种，就是一个矢量场的一个概念，一个矩阵的一个概念。后边这个 AB 是啥呢？你可以把它理解为 U0和 V0，就是在0时刻的这个 U0和 V0，然后那个矢量，再给大家看一眼那个视频啊，这个矢量，那这个矢量可以跟着向这个向
Most
量
of
场去
Hawking's
走。
vector field is going to be
哎，
described
对，
by a
你可以把这个粉色的这个向量想象成 UV，就是你的这个流速，然后这个背景的这个就是这个其实是个应变了，这是个应变场。这个应变场怎么影响你的这个你要考虑的这个流速？怎么把这个流速矢量给变化了？就是这么一段过程，你看是一模一样的。然后你可以看到，就是它就写成一个这个一指数上面放了一个矩阵的一个形式，这不就是李群吗？上面这个矩阵是啥？这不就是李代数吗？所以说，其实李群和李代数这个概念和物理海洋学关系是非常非常紧密的，只不过很多人都不知道而已。然后我现在在说，其实你也可以证明克氏力可以写成这么一个矩阵。你像这个，我把负号乘上去，这不是u 偏 t uv 等于正的 v，然后第一行是正的 v，第二行是负的 u，呃，对，第一行是正的 v，第二行是负的 u。你发现，哎，这个矩阵不是和这个旋度的这个矩阵一模一样吗？你就可以把它两个合并在一起了，就 f 加1/2 z 塔这个矩阵。所以说我们口口声声说的什么旋度也好，或者说你把它合并起来叫涡度也好，还有那些散度、法相应变、切相应变这些东西，它到底是什么呢？它是一个李代数前面的一个参数。你看，当它大的时候，那个向量场，你就想到那个向量场，它的那个每一个矢量，上面每一点对应的那个矢量都变得更大了。如果它小的话，那个矢量对应的也小。然后 F 为什么我们说 F 有效克氏频率是 F 加1/2 载它呢？啊，实际上就是因为它们两个都是这个矩阵前面的系数，所以当然就可以合并在一起了。有什么问题？没有任何问题。然后这里有个1/2，其实，我非常推荐大家就是在这个地方，真的你可以去推一推这个，就是怎么样从这个矩阵你把它拆成这四个，如果你只要做过一次这个，你就能立刻体会到为什么所谓的涡度是旋度的1/2，这个1/2到底是怎么来的，就再也不会为这个困扰了。但这个东西就是只可意会不可言传，你就亲自下笔算一算，你才明白这1/2到底从哪来的。然后继续讲，然后呃对，然后你看我刚才说了，这四个其实上都是这四个矩阵，你看散度、旋度、切相应变和法相应变这四个矩阵，其实都是李代数。那这四个矩阵构成了一个什么群呢？这个李代数构成了一个什么群呢？实际上就是大名鼎鼎的 SU2群，这里 S 代表特殊，U 代表有，这个以后我也可以介绍一下。然后单看这儿，你看泡利矩阵，泡利矩阵其实是一个很复杂、很出名的一个东西，很抽象，很难理解。那你看，这是维基百科上，他写了三个泡利矩阵，因为长这个样，长这个样和长这个样。他说，他们三个和单位矩阵一块张成一个2×2鄂米矩阵的向量空间。你就不要管这些专业术语，你就光看这个矩阵长什么样。你看这个，是不是和我这个切相应变这个矩阵长得一模一样？哎，这个和我这个旋度、涡度对应这个矩阵很像，它差了个什么？差了个 i，差了个虚数 i。然后这个呢，又和法相应变长得一模一样，这个单位矩阵自然就是散度对应的那个矩阵。你发现，哎，这不是一模一样吗？就是泡利矩阵是描述什么物理问题？是电磁学问题的。是一个电子的一个自旋的一个问题的。但是你看这四个，我们流体力学里经常谈的什么旋度、散度、地转流补散，然后什么亚中尺度过程，它的应变项特别大， 实际上它们其实真正的意义不是前面这个数，而是后面这个矩阵，是这个矩阵章程的这个向量空间，这个矢量场，这才是它真正的物理意义。所以说你就不要再用什么旋度的概念来去理解这个涡度了，它只是一个它只是一个数而已，真正的物理内涵是这个东西，就是这个矩阵代表这个向量空间。总而言之，这个李群和李代数，其实我感觉在物理海洋学里会有非常广阔的前景。就是我这里只是一个简单的介绍嘛，但是，我觉得这个东西就是你只要学一点点皮毛，可以说是对这些问题理解就有一个非常深入的一个理解。然后这本书也是我从那个海大图书馆找到的。其实崂山都没有人借这本书，这本书在虞山，我申请调过来的。然后你看这本书，它的简介上就写了，这本书是第一本将理学分析应用于深海内部的传播，并提出一种新的方法来描述深海非线性波的相互作用的著作。实际上，我在知道这本书之前，我就感觉李群这个东西绝对可以用在非线性波相互作用。你不光是波了，任何波流相互作用、流和流的相互作用、亚龙尺度和什么的相互作用，都可以用这个李群李代数的概念来表述。就是所以说，这个李群李代数这个东西，包括群和流行这个东西，我觉得是真的可以值得一学的。就是，你学一点儿点儿，你就可以对这些数学方法有一个更高层次的一个感受，有一个更直观的一个感受。我其实一直觉得咱们这个专业之所以让很多人感觉不到什么兴趣或者乐趣，很大程度上的一部分的原因就是咱们用的数学物理工具太原始、太落后了。我说真的，就是400年前的数学工具，它根本就，你看李群是什么年代的工具？是100年前的。群是什么概念的工具？是200年前的，不对，200年前的。但我们很多人都不了解过它。没了解过它，你说没了解过，是因为它和流体力学无关吗？和物海无关吗？并不是呀，相反，它和 n 次方程关系非常密切。你通过它能够更直观的去理解那个流速那个矢量到底是怎么样变化的，就像这个视频里展示的这样。这就是他们也管数学家也管这个东西叫流啊。所以说，我觉得真的学点儿这种数学是真的有非常多的好处的。总而言之，我今天的组会就讲这些吧。就是大家有什么问题的话，可以问一问，然后我尽力的回答一下。然后今天就这样，谢谢大家。有问题吗？没有问题。OK OK，那就这样结束。谢谢大家。